entropies.
Yes, good. Yeah, I'm sorry to keeping you from lunch with this long session. But anyway, let me tell you a few words about this result. It's with Ludovico and Marco, who are both here. Yeah, so we're interested in the entropy function, and in particular in its mathematical properties. And I think it's kind of instructive to start from the classical setting. So the slides are going to be very basic. Okay? I just want to convey some concepts. So classically, of course, entropy, most well-known entropy is the Shannon entropy, right? So we don't care about what it stands for. It's just about the mathematical properties. So the definition for a probability distribution for random variable is given by this term. Good, and then of course, as the title already took away, we're in particular interested in the continuity property of this function. And you could now look at like different distance measures in which you want to analyze continuity. One very operational one, I guess, this variational distance. So this is a well-known result that the entropy has this nice continuity property where the optimal upper bound is of this form epsilon times the dimension of the alphabet minus 1 plus this binary entropy function. And okay, I have all the references in the end if you're interested in them, right? I think this is usually attributed to Chisar originally. Okay, so this is a tight relation that in the sense that for every epsilon and x, dimension x, there exists distribution P and Q such that this becomes an equality. So this is very nice. And then there's this extension to conditional entropy. Of course, conditional entropy you can just write as the entropy of the whole thing minus the entropy of its part. But now what's very interesting here is that in this bound, you see here it's not the dimension of x times y, it's only the dimension of x. So the dimension of y doesn't enter, which is quite non-trivial, and it's also a more recent result. The proof is quite non-trivial as well. And for example, right, if you think about cryptography, y might be some adversary. So there are really uses for this bound where you want it to become independent of the side information. It could also be like continuous alphabet, stuff like that. Good. So basically, it's a very nice picture in a classical setting, and now we're interested in quantum generalization of these things. Of course, yeah, then the function is just the von Neumann entropy, right, of a quantum state. So very nice. Now again, continuity of this function. Okay, we look at continuity in the trace distance. Of course, you could look at other distances, but this is a very operational distance. And then the same result holds as in the classical setting. Yeah? You just get the same type of bound. And in fact, you can also kind of reduce the quantum proof to a classical proof. So you can kind of dephase the sigma in the eigenbasis of rho, and you can kind of lift classical proofs if you want. Okay? Good. However, if you now go to the conditional entropy, again, you can write it as the entropy of the whole thing minus the entropy of its part. Things become much less clear because it's not clear how to lift classical proofs. Okay, so this is the best known bound. It's called Alicki-Fannes or Alicki-Fannes-Winter. So Andreas actually improved it to this form. I think Milan also had some work on that. But okay, so what can we say about this bound? Well, so for starters, it's not exactly tight anymore, right? So if I give you a dimension A and an epsilon, there do not always necessarily, or we don't know, exist states rho and sigma such that this becomes an equality. Then the other interesting thing is here, maybe you have this A square, right? Whereas here you have an A. And if you want, you can think of this as the conditional entropy defined like this, right? It can also become negative, right? Takes values in between plus log A and minus log A. So this is kind of why you have to get a 2 here in some sense. But then you can also see, right, the bound doesn't necessarily take the same form. And I think it's kind of fair to say that we don't have kind of a general perspective or like full understanding of this bound. Good, so in this talk, I want to give you like kind of at least in some cases, an improvement on this bound and maybe some better understanding of what's going on. Good, so just very quickly, you might say, oh, why would we care? Why would we care to like slightly improve these bounds? And okay, fair point. However, I think there are a lot of like applications in quantum information theory, right? Because a lot of operational quantities, we actually write them in terms of the entropy. So for example, if you're interested in the continuity of channel capacities, optimal continuity, yeah, you can use these bounds. You can go to like entanglement theory, entanglement cost, gauge entanglement, these are entropic quantities. You can go to general resource theories, I look at transformation rates. So this is all kind of based on the entropy. Okay, and then you might say, okay, fine, but still, like, why would I care about tight continuity results? I have this one example that people studied in the literature, in particular this epsilon degrading channels by David and others. And here the point is, like, we don't really know what the quantum capacity of a channel is in general, and then, but one can give bounds, right? We always know that this coherent information is achievable, but then what are upper bounds? And one way of generating upper bounds is to kind of check how close your channel is to a degrading channel, because a degrading channel, for this, we know that the coherent formation is already the capacity, and then because you go a bit away, right, you find the next degrading channel, you have this kind of additional fudge term here, and this fudge term depends on the distance and some other parameters, but the point is, with this improved continuity bound, you can improve these fudge terms. You get better bounds on the quantum capacities of general channels. So that's one application. You can think of more, but I just wanted to kind of sketch one. Good. So what's our main result? So there's a neat way of stating it, which is actually not in terms of entropy or conditional entropy, but in terms of this kind of parent quantity, this relative entropy, right? And we call it a meta semi-continuity relation, and it looks as follows, okay? So you start with two states that are epsilon close and some third state omega, and then you look at, you want to bound the difference between the relative entropy of rho and omega, and then sigma and omega, right? So it's kind of relative to this third state omega. Okay, and then we can upper bound this distance with a term which has a very similar structure, right, as these tight bounds I gave you at the beginning. So it's just, instead of the dimension here, you kind of, if you want, you can call this like an effective dimension. You have this Dmax term, right? So I guess you all know how this thing is defined. Now the semi here in the continuity is just because there's no absolute value here, right? And here actually the rho appears. So it's not fully symmetric. It's not a fully continuity relation, if you want. Good. This is a bit of a simplified result, because if you have large epsilons, the bounds look a bit different. But the point is, again, this is tight, okay? So you can find, for every epsilon, you can find a triple of states, rho, sigma, omega, such as becomes an equality. Okay? So this is a nice form. Good. Now, of course, why do we call this relative entropy? Apparent quantity, well, it generates the von Neumann entropy, and it generates also this conditional entropy, right, if you look at these terms. So if you now take this relation, it has some immediate consequences for these two quantities that, you know, we're interested in. Good. So this is just the relation from the last slide. Nothing happened. Now, if we're interested in the von Neumann entropy, we actually get a slight improvement, which we have not found in the literature in this form, where now we get the same bound as before, but there's this additional parameter beta, which depends on the states. Okay, so now the right-hand side is improved, but in a way, of course, now it depends on the states rho and sigma. Right? But you can see that if there's just a maximal eigenvalue, right? If these are very mixed states, both these can considerably improve the continuity. Good. So this is more like I guess like a cute example for the von Neumann entropy, but it's also an improvement. And then for the conditional entropy, right? What do we get? Well, actually, in general, we don't get much. But if these two states happen to have the same marginal on the B system, and this is already a very non-trivial case, I would argue, then we get this improved bound, right? The previous one was this. Okay, so you can see that, well, the fudge term here is a bit improved, and here also you go from log a squared to a squared minus 1. Yeah? Okay. Good. And this bound was actually previously conjectured, amongst others by Mark, and okay, so it's conjectured also for general states, but at least now for these states with equal marginals, we can solve this. Good. Again, you might not care that much, but I think maybe the one reason you might want to care is because of kind of the proof strategy that we apply, and we heard a lot about these new integral representations that first appeared with the work by Frankel, and we're exactly using that framework to actually get these improved bounds. And what is nice about this proof structure is that they work equally classically and quantumly. So in some sense, we also have a new classical proof, but just immediately works in the quantum setting as well, because the proof is based on this integral representation, and this one equally holds classically and quantum. So I think that's kind of a conceptually nice point about the work. Okay, so I think you've seen this quantity a couple of times, or this representation over this week. So you can write this relative entropy as this kind of convex combinations of hockey stick divergences. And what is nice here is that these hockey stick divergences have very nice mathematical properties, which are even somewhat simple to prove. Yeah? And so basically, this representation, I think others made this point as well, this allows you kind of to lift properties from these hockey stick divergences, for which these properties are easy to prove, to the relative entropy function. Good. Proof sketch. What do we do? Well, we have this like, we want to get this meta semi-continuity relation, so this is we have this difference of two relative entropies, so we just plug in this Frankel representation of each one of them, well, in this hockey stick form, and then we order the terms. So here is one term with the 1 over gamma dependence, here's the 1 over gamma square dependence. And then kind of our guiding intuition for the proof is that we know that this continuity relation, at least for the setting of conditional entropy, it has to become an equality for these states. Yeah, if you look at the maximal entangled state and this slightly noisy maximal entangled state. So everything we do has to be an equality for if you plug in these two states and the corresponding omega. And so, yeah, this gives you kind of a tight handle of what you should do and what you should not do, I guess. Yeah. So then the trick is that you kind of you split up both integrals into three parts, and where you take the split off point depends on this the max entropy. Okay, and then for each, so you basically get 6 terms. So for each of those, you just bound the resulting terms using this elementary property of the hockey stick divergences. So for example, again, just one example, right? So if you look at this integral, and you look at it on this interval, right, the first one, so then the gamma is between these two things. So then you have to like upper bound this difference. And so one thing you can do is you can use this triangle inequality for the hockey stick divergence, and you can bound the first term by an epsilon. Well, the epsilon just comes out of the trace distance, that comes out of the triangle inequality, times this other hockey stick divergence, which then just cancels the second term. Right? So there's some nice simplification. And you can just do the same for all the 6 terms, taking this intuition, and you're done. So it's not an overly complicated proof. Good. So that's basically what I wanted to tell you guys. So this is this main result again, the conditional entropy version. And yeah, I didn't talk about applications. You can check out our paper. We worked them out. But I want to just show you one open question, which maybe some people here even know about. So let's go back to the classical case. What's the optimal continuity relation for the mutual information? Or even like, whatever, Shannon's channel capacity? I don't know. Nice problem. Can't solve it. Thanks a lot.
I think so. I hope it works. Does it? Okay, perfect. All right, thank you very much, Mario. So this is take 2 of this talk. I'm going to try and show you how we can get essentially the same continuity relation for this conditional entropy with the same marginal, but now using a completely different approach. So we're not going to use integral representations, but we're going to use what we call a very nice fundamental new entropic inequality, in which you will be able to see this quite quickly. This is joint work with quite a lot of people. Also quite a lot of them are here today. So yes. So I promised you a new entropic inequality. How does it look like? So maybe just let's set the setting. So we are going to have two states, which are epsilon far apart in trace distance. And now I can look at the difference between these two states, and I can decompose this into its positive and negative part. Something you can always do. Then you can have 2 positive operators that kind of satisfy this equation. And crucially, these 2 operators, delta plus and delta minus, will be orthogonal. So they will not share any support. And then if you know a bit how the trace distance works, you know that essentially it is just a trace of either the positive or the negative part here. And so what you can do then is you can look at these 2 operators, and you can say, okay, I want to normalize them, so I want to divide by their trace, which is just the trace distance between the 2 states. And then I end up with these 2 density matrices, so plus and or minus. And just kind of based on this calculation I just showed you, they will satisfy this relation. And that's essentially everything we need to write down on new entropy inequality, and it looks like this. So on the left-hand side, we have the differences between the entropies of the 2 states. And on the right-hand side, we have epsilon, so the trace distance, times the difference of entropies now of these renormalized positive and negative parts, plus the binary entropy of epsilon. And okay, this looks kind of very nice and cute. But you might ask, hey, why is it really useful? Because what do I ever really know about these entropy of the positive and negative part? Well, it turns out you don't actually have to know that much for this to be useful. So I just want to look at an example. So remember this kind of defining equation I gave you on the last slide. Now, because this rho plus and rho minus are orthogonal, and you can kind of see quite easily that if rho 1 is not equal to rho 2, then also always has to be positive and negative part. So this rho minus cannot be 0. So then in particular, the rank of the rho plus can be at most d minus 1. And so also its entropy can be at most the logarithm of d minus 1. And if we just use this and plug it into our inequality, then we can bound this h of rho plus here by the epsilon of log d minus 1. And then the h of rho minus you can just get rid of because it comes with a minus sign. And so we end up with this. And so that might look familiar, and then you maybe additionally realize that on the right-hand side here, if you exchange rho 1 and rho 2, then this doesn't change. So you get the same thing with an absolute value. And this is something that Mario showed earlier. It's kind of the continuity bound for the normal phenomenon entropy. And it's a non-trivial result, and it kind of follows almost immediately from this new entropy inequality. So in that sense, actually, there's something embedded into it. Okay, I'm going to give you more applications of this, particularly we're going to show this condition entropy continuity bound later. But for now, I'd like to focus a bit on the proof of this new inequality, because I think it's quite nice, and also somewhat instructive, kind of what really changes compared to previous approaches when people try to prove these continuity bounds. And I want to prove this quite elementary using just basic properties of the entropy. So what do we know about entropy? In particular, we know it to be concave. So if I look at a convex combination of states, then I know that the entropy of this convex combination is lower bounded by the convex combination of entropies. And okay, this is very, very famous, very well known, but it's not so hard to see that actually this isn't quite optimal if rho and sigma don't share the same support. So as a particular case, if we think of rho being orthogonal to sigma, then actually we know explicitly how to decompose this entropy. We know that the entropy of the convex combination we can write as the convex combination of entropies plus the binary entropy of this number that kind of defines the convex combination. And turns out you can kind of generalize this intuition. So if we introduce lambda, a parameter that is the trace of rho in the support of sigma, so this captures how orthogonal and non-orthogonal the two states are. In particular, if rho is orthogonal to sigma, this will be 0. And if they share the same support, this will be 1. Then we can prove this kind of improved concavity, which looks like this. So we have, again, the entropy of the convex combination on the left-hand side, the convex combination of entropies, plus the binary entropy, and then minus this additional term, which depends on lambda. And if you just have a quick look at this, so for example, if lambda is 0, then here I have binary entropy of q over q over q is 1, binary entropy of 1 is 0. This term drops, and you get back kind of this relation. And if we have lambda to be equal to 1, then p plus q here in the denominator is 1, so you have the binary entropy of q, which is the same as the binary entropy of p, because q is 1 minus p. And so you get back this normal concavity relation. Okay, that's nice. And then the additional thing I'll use is that the entropy is also almost convex, so it's not convex, but it is convex if you add this additional binary entropy of p on the right-hand side. Okay, and this is actually everything we need to prove our new inequality. And the proof goes like this. So I have what I'm trying to prove here up top. And then these are the two relations I just showed you on the last slide. And now it basically just comes down to picking kind of smart choices of p, q, and rho and sigma. And okay, so we want our state, so 1 over 2 to be epsilon far apart in trace distance. And I want to pick p and q here in my convex combination such that q is equal to p epsilon. I can do that if I make the choice like this. And then I can replace q with p epsilon everywhere. And I can also divide everything by p. And now I have to pick what I want to do with rho and sigma. And for the first line, I want to pick rho as rho 1 and sigma as rho minus. And for the second line, I want to pick rho as rho 2 and sigma as rho plus. And now you can remember this equation, which I showed many times already. So this relation between the rho plus, rho minus, and the 1 over rho 2. And then you will see that this left-hand side here is actually equal. And so we can bunch these two equations together. And we can see, okay, we have a term on both sides, which you can drop. There we go. And we can range terms a bit. And then we write for this. And this already looks pretty good. So we're almost there. We just don't quite have the binary entropy yet. We have kind of something slightly different, which depends on this lambda, which kind of now in this setting is given by this. It's kind of the definition of lambda now if I plug in what I chose for rho and sigma. And again, if you remember this relation, then it's not so hard to see that this lambda plus epsilon here is upper bounded by 1. So in particular here, if you kind of plug in rho 1 here, then you'll see you get a rho plus, which cancels with the support of rho minus because they're orthogonal. You get a minus epsilon, and then the trace of O2 is upper bounded by 1, so you get this relation. And then you can use in the cavity of the binary entropy to see that this whole term here is actually bounded by the thing we're trying to get. The trick here is that you do a convex combination with the binary entropy of 0, which is 0. And that's all we need. And maybe if you, kind of a side remark, if you remember the relation that Mario showed earlier, kind of what people like Andreas have proved previously, they always have these kind of slightly worse terms of 1 plus epsilon, binary entropy of epsilon over 1 plus epsilon. Kind of the key improvement here is really to kind of use this better concavity that in the end gives you something that you can upper bound just by the normal binary entropy. Okay, so this is our new bound. And we can use this to prove better continuity bounds. And we get something very similar to what Mario showed you earlier. So in particular, we get something for the relative entropy, which we then can use to get a bound on the conditional entropy. The relative entropy bound looks slightly different. So again, the setup is the same. We have two states which are epsilon far apart in trace distance, and we have the same state sigma here in both relative entropy expressions. But the bound, we don't get a ρ1 or ρ2 here, but we get this ρ plus in the Dmax. In general, I don't think there's any way to kind of relate these two quantities. They can be different in both ways. But then for the conditional entropy, we kind of, get the same trick in bounding this, and we get the same bound here. So if the marginals are the same, then we can get this bound with the dimension squared minus 1 and just the binary entropy. And actually, I'd like to show you how this goes, because it's kind of very similar to the thing I showed at the beginning, how you get the ordinate fineness inequality just from a new bound. So previously, kind of some of the trick was that if we have two states which are orthogonal, and I look at this difference in entropies, then okay, one of them I can just drop, and the other one I know has to be bounded by a logarithm of d minus 1 because it can't be full rank. It turns out you can do something very similar for relative entropy. So if you have, again, two orthogonal states, and I look at this difference of relative entropies with the same state sigma, then you can do like a small pinching argument to show that you get this bound. When instead of the dimension, you have this e to the d minus. And using this, we can just then prove this relative entropy continuity bound, just essentially using the definition of relative entropy. So relative entropy you can write as minus an entropy term minus trace rho log sigma, and then if you look at the difference, you get this expression. And then here on the right side, I can again use this relation between the ρ1s, ρ2s, and the plus and minus. And for these two entropy terms, I can use our inequality. I kind of, there's a minus here, so I'm using it with where I've reversed ρ1 and ρ2, but that's okay. It doesn't change anything. And then you realize that the thing you end up with here is nothing else than just epsilon times this difference of relative entropies. Then you use the lemma up top, and then you get what you're trying to show. So again, it's very simple if you have this surprisingly powerful entropy inequality. Yeah, that's it for my side. Maybe a few remarks at the end. So not the continuity bound because it has a dimension, but this entropy inequality, which I showed at the very beginning, we can show also in infinite dimensions, which is nice. And then open questions, yeah, Mario already mentioned it. We'd like to prove this for the general case, where the marginals are not the same, but we don't know how to. And kind of very similarly, but even more generally, it would be very nice to get good upper bounds on this generic difference of relative entropies. Also second state changes. We have a bound like this in our paper, but it doesn't depend very well on the difference between sigma 1 and sigma 2, so it's not tight in that regard. And we'd like to have something which is just tight. So thank you very much, and of course ask questions if you have any.
Okay, thanks Björn, thanks Mario. So you can ask questions to the two of them, even to Mario. I mean, who's not on the stage?
Yeah, thank you for the nice talks, both of you. Do you know in what operational setting your bound would be outperforming Mario's and others' bounds, or is that not at all clear? I mean, you have this Emacs thing there.
If you're very honest, then Mario's bound is usually easy to calculate because you don't have this kind of weird, positive part here. I think we checked this numerically, and at some point you can find some states where either is better, but I can't really give you like a super concrete operation.
Okay, thank you.
Thank you for the talk, Bjarne. And Marius, this improved inequality that you have, this reminds me a bit of there's a continuity bound for the optimized sandwich conditional entropy by Salman from a 2023 paper. Can you comment a bit on this? Did you look into this? Do you know how this compares and how it's different? Because there I think you can't take the limit alpha goes to 1 to recover sort of what you get, but to me it seems very similar.
Okay, I don't know this paper well enough on top of my head to really say something concrete, or maybe we can talk about this afterwards. Yeah, I think I'm definitely interested, but I don't really want to say something wrong here.
Hey, thanks for the talk. So, but do you think like that we can get the full case of the continuity relation for the conditional entropy from a relation like that from like for the relative entropy, like the one you showed on the last slide? Because it seems somehow, so, okay, so what would be an upper bound on this difference of two completely general relative entropies? If you have only control on the first argument, it doesn't look like it should.
I mean, you also have to impose some constraints on like the trace distance between the sigmas.
Yeah, but for the conditional entropy, the key point is that they vary in the same way, right? So,
yes, yeah.
So somehow, I don't know, this looks too general, maybe?
I mean, it does. I guess, I mean, I'm interested in this also in more general cases, because, you know, you have plenty of cases like channel discrimination where you have things like this and you care about continuity. But, I mean, I suppose if you have a really good bound on this, maybe it would imply this. I don't know. I don't want to rule this out.
But no conjecture on what the form would be?
Not really, no. I mean, you can write something down, but it's, yeah, no, I don't know.
What about other distances, like not TV distance? Because I remember that Giacomo had this continuity bound with the Wasserstein distance. So, I mean, can you also do something better in that direction?
I mean, this approach really kind of very strongly relies on the fact that this decomposition kind of really corresponds to trace distance. So, yeah, unless you want to get loose bounds by using some kind of full relations between distances, I think you have to do something different.
I was wondering whether any of the two continuity results, like for conditional entropy, can be proven. Suppose we wouldn't know that Strong's additivity is true. Could you prove one of the two without them? Because, okay, for this one, I always thought, but maybe I'm wrong, that this almost convexity property of the entropy, at least the proof I know, uses Strong's additivity.
Yes.
So then one would... Okay, if there's not another proof, then I would say your bound clearly needs Strong's additivity somewhere under the rock. And I was not sure whether the integral representation by Frankel also needs it. I mean, it's not an important question, but I was just wondering. If you want to teach it, for example, once, which one would be conceptually simpler?
Well, I don't know. I guess, I mean, the proof also uses data processing on quite a bunch of steps under the hood.
Okay.
And I mean, that's the equivalent of Strong's additivity. In that sense, you're not really... I guess you're using it also in other ways, maybe that's less obvious. I think the integral representation also kind of like, in some sense, implies data processing, so it's not so obvious, I guess, how...
Once you have the integral representation, right, all kinds of properties go on.
I know, yeah, I know.
So in that sense, it's cheating, but in the other sense, it's a couple of properties of the hockey stick cover, this is enough.
Okay. Cool, okay, last question.
Thanks for the great talk. You say your bounds is applicable to infinite dimensional case, but for the bounds between rho and sigma, at some point, so sigma can be arbitrary, but you need to, usually for the semi-continuity bound, you need to impose some energy constraint thing for rho.
So what we show is this. This we show to all infinite dimensions. We don't talk about continuity. Because, you know, in the actual continuity bound, there's always a dimension in the end. And we're not, like, you can fix this as energy constraints, but that's not what we're doing. What we're trying to say is this bound, okay, you have to be a little bit careful. You actually want to move this to the right side and this to the left side to make sure you don't get infinity minus infinity. But in that case, kind of this thing still holds. And then, you know, you can maybe use this to prove some special continuity bounds, but like the actual like proper continuity bound, we don't say anything about in infinite dimensions.
What I thought was d max of rho plus should be finite. I mean, for here maybe for bounds for d max, I mean dd, you need to ensure that d max of rho plus should be finite. But my question is essentially, is this stronger or weaker compared to conventional energy constraint assumption? But maybe
I think,
you haven't thought of that.
I don't think there's kind of an obvious relation between this. I think
This is worse than what Andreas has with the energy assumptions, the continuity relation, because this Dmax is kind of like not an average energy thing, but like a worst case thing.
Yes. Thank you for clarification. Yes.
I guess also we don't really specify Hamiltonian or anything, but okay.
Okay. So Andreas has an announcement, but before let's thank Bjarne, Mario, and all the other speakers.